Now, a couple of these I did not review with you. The power of a product. I can show you why that one works if you'd like. But I think that's pretty straightforward. Quotient of powers we went over, and then the last one, the power of a quotient. It's one of I did not review that one with you as well. But if you have a fraction that's raised to an exponent, you can raise the numerator and denominator to that exponent. Awesome. Now, I anticipate the struggle for you guys being that all of these exponents are fractions. And I don't know that we love to operate with fractions. All right, last thing as you guys wrap up. When you multiply fractions, do you have to have common denominators? No. Multiply fractions. Where's our example? I don't know if I have any up here. Oh, there it is. What's 5 halves times 2? Well, 5 over 2 times 2 over 1. Like right here. Power to power, didn't you multiply? 5 over 2 times 2 over 1. Isn't it 10 over 2? What's 10 over 2? 5. That's why it's 5, right? So multiply fractions, you don't have to have common denominator. Adding fractions, yes, of course. Subtracting fractions, yes. You just remember you keep the denominator. So 5 halves minus 1 half is 4. Did I write 1/4? 5 halves minus 1 half is 4 halves, which is 2. Questions on the properties before we do some examples? I will tell you what, I'm going to leave that frozen up on that board over there. We'll do an example on this one in case you're still writing. All right. I have the same bases. I'm multiplying the bases. What do I do with the exponents? Add them. Good. When I add 1/4 plus 1/2, do you know what that is?
3/4.
3/4. Good. Now, if you don't know that, you have to make them both common denominators. 1/4. How many fourths is a half? It's 2/4, isn't it? Add them together. 1/4 plus 2/4 is 3/4. Good. And again, don't let the fraction exponents bother you. If you ever forget that, go back to your x squared times your x cubed. Everybody in the room knew that was x to the 5th, right? You add the exponents. Go back to a simple example that you know. All right, next one. We're going to use what's called they call it the product property. What do they call that one? Power of a product. Power of a product. You notice if you have the power power of a product. Product means to multiply. Then you can raise each of the terms to that power. So if I use that example here, wouldn't I raise 6 to the 1/2 to the second and 4 to the 1/3 to the second? What's 6 to the 1/2 squared? Oh, it's easy. You got that. What do you do with the exponents? Multiply. What's a half times 2? 1. Just 6 to the first. Just 6. Times 4 to the... What's the third times 2? 2/3. And you would leave it like that. Next one. We've talked a little bit about negative exponents, right? What happens when you have a negative exponent? You need to make a positive by?
Putting it over 1.
Good. Putting it in the denominator if it's in the top, or bringing it up to the numerator if it's in the bottom. Okay, so you could do a couple different things. Option one is to drop that whole thing to the denominator and make the exponent positive. Okay, so we have a 1, and I dropped that whole thing to the denominator. I made the 1/5 positive. Option 2 is to use what we just did, was the product property, the power of a product. So we would raise 4 to the 5th to the negative 1/5 and 3 to the 5th to the negative 1/5. Simplify it and then finish it off from there. Make sure all the exponents are positive. So now let's keep going with number 1. We're going to have to use that, what was it? Product, power of a product, is that what they call it? Yeah. Power of a product. So I have 4 to the 5th, but now it's to the positive 1/5, times 3 to the 5th to the positive 1/5. When I have a power of 5 raised to the 1/5, I multiply them. What's 5 times the 5th? 1. So it's 4 to the first power. Yeah, just 4. I'll put to the 1 just so you can see what happened. And then 3 to the first power. And then we just do 4 times 3 in the denominator. 1 over, what's 4 times 3? 12. So 1/12 will be our answer, doing method 1. All right, option 2. I do the power of a product. I have 4 to the, careful, what's 5 times negative 1/5? Negative 1. 3 to the negative 1. So if I see a negative exponent, you said to make a positive by dropping it down to the denominator. I would need to put 1 over 4 and 1 over 3. Now the exponents are positive 1 for both the 4 and the 3. And what's a 4th times a 3rd? 1/12. Good. So either way, you should get a 12, right? All right, next. I see the division of two things. They both have a base of 5. What's the exponent on 5, though? 1. Exponent on 5 down here? 1/3. What's the property if I divide bases? I do what with their exponents? Subtract. So it's going to be 5 to the, it's going to be 1 minus 1/3. 1 minus 1/3. Positive, negative? What'd you get, Martin? Positive 2/3? You guys all agree? If you really don't know, you would do make common denominators. We have 3/3 minus 1/3 is 2/3. So we get 5 to the 2/3. Now, for one like letter E, there's a couple ways you could do it. One of the properties says we can raise the numerator to the second power over the denominator to the second power, right? Another property says we could divide. If they have, don't they have the same exponents?
Mhm.
Can we divide the 42 and the 6? Let's go back and see if we have a property that says that, right? Do you see this one down here? If you have a base, and it doesn't even have to be the same base, a base to an exponent of m over a base to an exponent of m, you could write it as the division of those bases to the same exponent of m. Now let's see how that would apply here. How would I rewrite the inside using that property?
You would do like 42, 2 times 1/3, 2 times like 1.
Yeah, that's one option, is to raise them both to the second power over the second power. But what if I want to use the inside? Ignore the 2 for now. If I want to rewrite the inside, how can I rewrite that?
7 to 1/3.
Very good. Isn't this an a to the m over a b to the m, where a is 42, b is 6? They both have an exponent of 1/3. That is a over b to the m. Well, what does that look like? 42 over 6 to the 1/3. Now, the nice thing about that is I know what 42 over 6 is. What is it? 7. So it's 7 to the 1/3. That's just addressing the inside. I haven't taken care of the exponent on the outside, right? What's the exponent on the outside? 2. So I would still need to raise this to the second power. What do I get when I do that? 7 to the 2/3. Good. I'm going to pause and make sure you guys hear me clearly on this. You're going to get mixed up and confused when you look at problems, okay? There's so many properties that look similar that you're like, is that one of them? We're not really fluent with these right now. So you're going to need to have these guided notes with you, and that box that we wrote down at the very beginning to see and test and say, oh yeah, that's a property, or no, that's not. I don't think that's one of the properties. Does that make sense? Don't just try to do this going blind, all right? Use your notes for this. All right, properties of radicals. Good news. A radical, it's written differently, but it's just a fraction exponent, okay? So if I say the square root of x, isn't that x to the 1/2? And if I say the cube root of x, that's x to the 1/3. So as we go through these, all you're doing is using the same properties we've been doing. But I want to review something with you real quick, all right? So do you see what they did here? They did 4 to the 1/3 times 2 to the 1/3 is 8 to the 1/3. They just used the property. But they're writing it in radical form for a reason. All right. This is going to get a little tricky. I need you guys to focus with me here. All right. Why can we write the square root of 36? Why can we say that's 6? Well, let's go back to the basics. What do you look for under square roots? You look for pairs, right? Now, remember earlier in the year, I told you could stop if you got this, right? Weren't students tempted to do this? pair of 2s, pair of 3s. Weren't they tempted to keep going? But what happens when you get a 6 times 6? What's another way to write that? 6 to the second power. And when you square root something squared, you get the number inside, right? You get 6. What do you think you're looking for under cube roots? Yeah, good. We're looking for things to the third power, right? What makes up 54? Well, I'll give you a hint. 2 times, what's half of 54? 27? 27 is 3 times 9. 9 is times 3. What comes out? Isn't this 3 cubed? I'm taking the cube root, right? When I cube root 3 times 3 times 3, what comes out of the cube root? A 3. Very good. What's left inside the cube root? Do you agree that would be written in simplest radical, where we're talking about cube roots, form? Do you understand that? Yes? So, we're going to be simplifying radicals here in a minute, but I want to make sure you guys understand that. If you have a fourth root, you're looking for groups of 4, because it would be to the fourth power, right? And a fourth root cancels out a fourth power, just like a square root cancels out the power of 2. All right. I'm going to look in the book to see how they want us to, for this one, if they want us to break it up first and write it down, or if they want us to multiply it out and then break it up. I'm tempted to write these in radical form first. Let me just double check so I don't lead you astray. All right, cube root of 12. This is example 2. What do you get when you do, what if we were to multiply 12 times 18? Here's what I would be tempted to do. Okay, calculators out. Take your calculators out. Do 12 times 18. You get the cube root of 216. And then the first thing you should ask yourself is that a nice cube root? I'll try to take the cube root of it. What'd you get? 6? Perfect. Now, what I was tempted to do, and this is, it's not wrong, it's just different. It's a different way to do it. If you were to try to break this up, isn't 12 4 times 3, and 4 is 2 times 2, right? I don't see any cubes coming out of that thing, do you? Right? 18 is 6 times 3, and 6 is 3 times 2 times 3. That makes up 18. I don't see any cubes coming out. So another option would be to try to break these up individually and then multiply them together. But that was a nice, perfect cube. So that was the easiest way to do that one. If it didn't work out that way, you'd have to try a different method. Question, Madeline? You good?
Oh, no.
All right, next one. It looks like a fourth, I mean, it's a fourth root, but doesn't it, can't we also write that to the 1/4 power if we really wanted to? Using one of those properties from earlier. So a couple options. Just like we did on the previous problem, try to divide 80 and 5 first and see if we get a nice fourth root. That would be the fourth root of, what's 80 divided by 5? 16. And is the fourth root of 16 a nice whole number? What times itself, times itself, times itself is 16? 4. Careful. 2. right? Let's double check. Here's the tempting part. Ooh, a pair of fours. A pair of fours. Nope, we're not looking for pairs. We're looking for something to the fourth power, right? Oh, there's a group of 4 2s. That's 2 to the fourth. So the 4 through to 16 must be 2. All right. So how do we write things in simplest form? You need to pay attention to this and use this as you go through the homework. This is when you can tell if your answer is in simplest form. No radicands have perfect nth powers as factors. Okay? What a radicand is the inside of a radical. Okay? So if you left it as the 4th root of 16, this is saying that's a problem. Because the 16, watch up here, I'm going to walk you through the vocabulary. This vocabulary is kind of confusing. Watch up here. The radicand, 16, had a perfect 4th root, didn't it? Wasn't okay to leave like that. No radicands contain fractions, so you can't have a fraction under a radical. No radicals appear in the denominator. Ooh, that's going to be a little tricky here in a minute. We're going to have to rationalize the denominator by multiplying by something. We'll show you that in a minute. All right, write the expressions in simplest form. All right, go ahead and break down 135 into a nice form that might be easier to write it in radical with a cube root symbol. Simplified. I'll give you a hint. Do you remember when we simplified square roots, we tried to pull out the biggest perfect square that we knew went into it? Yes. What do you think you want to try to pull out in this one? The biggest perfect cube? What are our cubes? Quick little refresher. What's 1 cubed? 1. What's 2 cubed? 8. What's 3 cubed? 3 times 3 times 3. 27. What's 4 cubed? 64. Good. And what's 5 cubed? 125. Those are your perfect cubes. If you can find one of those numbers going into 135, you're well on your way. Anybody find one of those going into 135? Now.
I did 3 times 45 and 9. I broke it down into 5 and 9 and 3.
3 times 45. And then what?
5 and 9.
5 and 9. So what do I see here? I see what comes out? And then we have what's left? So how would you write that? 3 times the what? The what? Cube root of 5. Anybody find a different pair to break it down into?
5 and 27.
So 27. Oops. (27) and 5. Now, at any point, do you guys agree what I'm really writing here is the cube root of 27 times the cube root of 5? All right, isn't that the properties we use to do this? It's the cube root, but they're still underneath the cube root, right? They haven't come out of the cube root yet. And then at any point, if you stop and you say, oh, I know the cube root of 27, it's 3. The cube root of 5 is a decimal, right? You could do that. Just like when you did square roots. Let's say you had a 2 times a 64. 2 times a 64. Don't you know the square root of 64? You could stop and say, oh, 2 times, or the 2 stays inside, and then the square root of 64 is 8, right? So you can stop along the way if you see perfect cubes. All right, is letter B completely simplified? No. What's the problem? Which of those bullet points does it fail, Martin? Very good. How do you get rid of a radical in the denominator? I'm glad you asked. I didn't ask. Let's review what we would do typically. Ready? Here's another example. I'll call it example B with a little I. I don't know why. Just whatever. What if I had radical 2 over radical 5? I asked you to write it with no square roots in the denominator. What would you multiply top and bottom by? By what? Close. Remember rationalizing the denominator? Remember doing that? Radical 5 over radical 5. Does that change the value of the problem? What's radical 5 over radical 5? Careful. Is multiplying by 1 changing the value of the problem? No, it just makes it look different. Okay? What's radical 2 times radical 5? Radical 10. What's radical 5 times radical 5? Radical 25, which is 5. We just got rid of the square root in the denominator, didn't we? Why did we choose to multiply by radical 5?
Because it was the denominator, and you can't have radicals in the denominator.
Good. For radicals, a pair gets rid of the square root sign. Do you agree? Yes? A little foreshadowing here. You ready? Careful. I'm not going to multiply by the 5th root of 8 over the 5th root of 8. I'm not going to multiply by the 5th root of 8 over the 5th root of 8. Not by radical. Well?
Would you multiply by radical?
Not radical 8. What will get rid of that 5th root in the denominator? Don't write this down. I'm going to do the problem wrong. I'm going to show you what would happen if you did it wrong, okay? If I multiply by the 5th root of 8 over the 5th root of 8, that's 1, right? I'm not wrong, and I'm not changing the value of the problem. But is that going to help me? What's the 5th root of 7 times the 5th root of 8? The 5th root of, what's 7 times 8? What's the 5th root of 8 times the 5th root of 8? The 5th root of, do you know the 5th root of 64? And even if I broke it up and found not pairs, not groups of 3, not groups of 4, groups of 5, are there any groups of 5 in there? Go ahead, take the 5th root of 64. So did I get the radical out of the denominator by multiplying by the 5th root of 8? No. That didn't work. What would have to happen when I multiply these? Whatever it is in the denominator, it's going to be the 5th root of something. What's going to have to happen to get rid of that 5th root symbol? When I multiply them together, the result is going to need to be a perfect, not square, but 5th, something. Well, what are those? What's 1 to the 5th? What's 2 to the 5th? Two times 2 is 4. 8, 16, 32. Ooh, I could get a 32 here, couldn't I? I could get a fifth root of 32 here, couldn't I? What do I put inside the fifth root?
4.
A 4. Well, if I do it in the bottom, I have to do it in the top. What's the fifth root of 7 times the fifth root of 4? The fifth root of 28. I don't know that, but that's okay. I don't need to know that. My goal is to get rid of the root in the denominator, right? I get the fifth root of 28 over, what's the fifth root of 32? 2. Did I get rid of the root in the denominator? Yes. That was tricky. Why did I pick 4 in there? The fifth root of 4.
It multiplies to 32. 8 times 4, 32.
Yeah, and it multiplies to make a perfect fifth root. I know 32 is the fifth root. Fifth root of 32 is 2. Let's do, I'm going to do, while we're at it, let's do letter D real quick. While it's fresh in your mind, I want you guys to try that one. Do you know the fourth root of 4? Because if so, just simplify it. What's the fourth root of 4? Is that a nice whole number?
No.
No. All right, what do I multiply top and bottom by? Huh?
4.
Just 4?
4.
Fourth root? Fourth root of 4? I do it in the bottom? I do it in the top? Jaden, why'd you pick the fourth root of 4?
That's the second. 2 to the 4th is 16.
Good. He knew if you multiply the fourth root of 4 times the fourth root of 4, you get the fourth root of 16. And we know the fourth root of 16. What's the fourth root of 19 times the fourth root of 4? 40 and 36. That's fourth root of 76? So we get this, the fourth root of 76 over 2. Now, I would like for you guys to try to simplify the fourth root of 76 to see if it can be simplified. Not just type it in your calculator, but see if any groups of 4 come out of it. Did you get 2 times 2 times 19? Any groups of 4 come out? No. So that is simplest form. Now, are you always going to multiply by the fourth root of 4 in the denominator? Not always. If this was the fourth root of 3, we'd have to pick something different, okay, to make it one of these perfect numbers to the fourth power. All right. I'm going to skip letter C. One more thing I need to teach you. is you can't have roots in the denominator, okay? So we're going to multiply something by a 1 in disguise to get the square root out of the denominator. I'm going to give you a hint. We're going to multiply by, it's called the conjugate pair. So opposite sign. So we're going to multiply by 5 minus radical 3 on the top and bottom. Well, 1 times 5 minus radical 3 is just 5 minus radical 3. We now have a square root in the numerator, but that's not a problem. There's no issues with square roots in the numerator. The denominator, we're going to have to FOIL to simplify. Five times 5, 25. Minus 5 times radical 3. Inner, the I, plus 5 radical 3. And then the last, minus, what's radical 3 times radical 3? 3. If you said radical 9, that's fine, but that radical 9 is 3. Square root of 9 is 3. Well, what now? What's 5 radical 3 minus 5 radical 3? Cancel. We get 5 minus radical 3 over, what's 25 minus 3? 22. Did we get the square root out of the denominator? Yeah. The reason that it's called the conjugate pair, the reason the conjugate pair is always going to get rid of that square root is because when you change the sign between them, in FOIL, aren't the O and the I going to always cancel each other out? And those are the ones with the square roots in them. Okay? So that's the trick to get rid of that. So in the next one, we're not going to do this one, but what would you multiply by in letter B? Radical 7 plus 2 on the top and bottom. Okay? That's a lot of info today. All right, we're going to spend another day on that tomorrow.